its applications and its properties. So ultimately, these are the three things that we are going to discuss in this branch. Got it? So what do you mean by light? This is what we think of. What do you mean by light? Light is a form of energy that gives us the sensation of vision. Light is a form of energy that gives us the sensation of vision. Sense of vision. Sense of vision means the ability of seeing the bodies in the nature. The ability of seeing the bodies in the nature. That is called sense of vision. Okay, so you need to listen to me briefly, just like shorthand notes, so that you have to keep writing. Okay, so please don't wait for my dictation. Got it? Okay, so sense of vision. This is the value point over here. Sense of vision. What do you mean by sense of vision? The ability of seeing the bodies from the nature. The ability of seeing the bodies from the nature, that is called sense of vision. That is called sense of vision. Sense of vision. Got it? Okay. Now, so there's anything that we see in the nature, if at all you want to see that particular object, light is very much essential. Without light, passage, seeing the bodies in the nature is not possible. Seeing the bodies in the nature is not possible. Got it? So in what way? So there's if at all you want to see this piece of chalk, okay, so what happens from the source? Light has to travel on this piece, there's a piece of chalk. Got it? So light has to undergo reflection. Okay, that reflected light has to reach your eye. These reflected light rays will have to form the image on the retina. Got the point? Okay, so from the retina, optic nerve will be there. That optic nerve will be converting that image into electrical signals. Through the optic nerve, the electrical signals are sent to the brain because brain cannot see. Brain can read only electrical signals. Any information you give to brain, brain's reading will be in the form of electrical signals only. And if at all, so you touch any hot surface, very hot surface, in which your hand is getting burnt, even that burning sensation also will be sent to the brain in the form of electrical signals only. And if at all you get any pain, you just stamp on a thumb, immediately you will get pain. But the point, even that pain also brain will read in the form of electrical signals. Got it? Okay, so this here, optic nerve will be converting that image in the form of electrical signals. Okay, and in the form of electrical signals, so what happens? So this here, so brain, will analyze what kind of image has reached. Immediately, there will be some history lobe over here. Okay, brain will link up that history to the image, to the electrical signals. Immediately, brain will analyze, oh, this is the object this fellow is watching. And this is how you have to respond. Got the point? So this is in this way, this is you need to respond. That command will be given by brain, by motor nerves. So not only that, so that's which part has to be responded, even that thing also brain will tell. Hello? Class started. Okay, got it? Understood? So what I'm telling is, so immediately brain will tell, how we have to respond. But the whole process will take place within the fractions and fractions of seconds of time. Whole process will take place and will get completed within the fractions and fractions very fast. But sometimes even this brain speed also may not be sufficient for us. In such cases, this third part of the brain, which is medulla oblongata, will come into the picture, which is reflex actions, involuntary actions. And whenever we meet any dangerous situations, so brain will take some fraction of second of time. Even that fraction of second of time also, should not be. Otherwise, so that's you will meet with accidents and other things. But the point you are driving, immediately all of a sudden there's here one more vehicle has come to hit you. So fraction of second, not even a fraction of second, milliseconds, microseconds. Immediately you will not be staying like that. Within no time, you will be responding, you will be turning your vehicle, aside to save yourself. Are you getting my point? In such cases, this large brain, small brain will not come. Cerebrum, cerebellum, those things will not come. into picture, medulla oblongata will come. Because this, gives, this senses very faster than these two, cerebrum and cerebellum. Are you getting my point? Are you getting my point? Okay, so for this entire process, into our eyes, something has to enter. That something is nothing but light. Something has to enter. That something is nothing but light. So, light is the form of energy that gives us the sensation of vision. Light is a form of energy that gives us the sensation of vision. Sensation of vision. Understood? Like this. Okay. So next, it's the properties. It's the properties. So what are the properties? In this nature, so light exhibits some of its own properties by means of which the complete, so natural phenomena take place. In what way? The very first one is reflection. In fact, without that reflection, seeing the bodies is not at all possible. Got it? So the second one is refraction. Refraction has got many applications in our day-to-day life. Even natural process, atmospheric refraction also takes place by means of which, early sunrise, delayed sunset, all the things we take. Got the point? And the rainbow formation. Rainbow formation. So many amazing things that take place in the nature. All those things are just because of these light properties. Got it? And the next one is, so interference of lights. Interference of lights. Diffraction of lights. Polarization of lights. Dispersion of lights. Total internal reflection. So this here, these are the properties which light exhibits. For that, our involvement is not required. And these are the properties which happen in the nature naturally. They are naturally occurring processes. They are naturally occurring processes. Got it? So they are called properties. Next, applications. So what do you mean by applications? What do you mean by applications? Applications means uses. So by using these light properties, we have developed some of the devices and all the things. The best devices, microscope, telescope, binoculars, even, that's a cinema, and the cinema screening and all the things, they are nothing but the applications of this light. Got the point? So by using the light properties, take reflection. Based on reflection, we developed, some of the devices. And by means of those devices, we are getting so many practical applications in our day-to-day life. Day-to-day life. Got the point? Refraction. We have so many applications. Interference. By means of interference, so this here we will be able to measure the thickness of very, very thin films and other things. In the industrial field, whatever measurements people carry on, people take up, all the things are just because of these properties of light. Understood? Telescopes, microscopes, all the things become applications. So all the things we have to discuss. So ultimately, what about the optics that we are going to discuss? This optics is of two approaches. So the first approach is ray optics. The first approach is ray optics, and the second approach is wave optics. And the second approach is wave optics. Ray optics and wave optics. And what is the main difference between these two approaches? In the case of ray optics, the complete propagation of the ray, that's a light, is dealt on the basis of ray. And what do you mean by ray? Ray is nothing but the collection of so many particles. In fact, the ray concept has come out of Newton's corpuscular theory. For the propagation of light, in fact, two important theories were developed. So what are they? So the first one is corpuscular theory. The first one is corpuscular theory, and the second one is wave theory. These are the two theories which were developed. These are the two theories which were developed: corpuscular theory and wave theory. Corpuscular theory was proposed by Sir Isaac Newton. Sir Isaac Newton, remember. So that's you will be having theoretical applicative questions, I am telling you. But by each and every conceptual knowledge has to be there in your mind, not only solving the problems. If at all you are very good at solving the problems, I say that perfection is up to 50% only. Remaining 50% conceptual knowledge is very, very important. Got it? So this corpuscular theory was proposed by Sir Isaac Newton in the 16th century. corpuscule. In the Latin language, corpuscule means that is particle. Okay, so according to him, light is something which spreads in the space in the form of particles. And if at all you take any source of light over here, and so if at all you take one particular path along which light passes. Okay, so in this path we can have as many as minute particles. There will be so many minute particles present in this. There will be so many minute particles present in this. Okay, the collection of all these light particles is nothing but ray. This is called a ray. Ray, in the sense, it's a straight line path along which the light energy is confined. Very narrow ray. And so many such rays, millions and billions of rays will combine together. Then one beam of light comes. A beam and ray, both things are not equal, are not the same. So a beam of light means it's a collection of so many, light rays. So many light rays. But the point of like this. Okay, so this here, due to some reasons, this corpuscular theory was failed. Okay, so what are those reasons? That also I will tell you. Okay, so this here, according to this, so there's a reflection of light successfully he could explain. But the point, even refraction of light also successfully he could explain. Okay, so in what way did he explain? What about the particles which are presented in the light ray? All those particles are elastic by nature. All these particles are elastic by nature. Elastic in the sense just like a rubber ball. When you hit the ball onto the surface, what happens? The ball bounces back. How the ball is behaving, so in the same way light particle behaves. Okay, so light particles will be having some elastic nature. So if you don't take any surface over here, so when you incident light ray over here, in this there will be so many particles. The moment the particle hits the surface, with the same momentum, the particle will be bouncing back. And what about the rebouncing nature? The particles exhibit over here. That is nothing but reflection. In that way, he could explain. Okay, that was convincing. And coming to refraction. Refraction in the sense of bending of light ray as it passes from one medium to the other. One medium into the other medium, when the light passes, if the separation of two media, a kind of bending takes place. That type of bending is known as refraction. But, medium, we are taking. Medium means medium's density matters a lot. That density will affect the velocity of light particle. Okay, so according to Newton, if you take a rarer medium, means less denser medium, that is called a rarer medium. According to Newton, in the rarer medium, the light particles will be moving slowly. The speed of light is less. Okay, so according to Newton, if you take a denser medium, denser medium, through the denser medium, the speed of light is more. That's what he performed. Later it was disproved. But according to Newton, rarer medium, when the density is lesser, speed will be less. Slowly the particle will be moving. Where the density is more, because of cohesive forces, adhesive forces, the speed increases. Because it's a particle. Particle means matter. That was Newton's argument. But wave theory disproves. According to wave theory, speed of light is more in rarer medium. Speed of light is less in denser medium. In fact, practically, experimentally, the same thing was proved. Experimentally, that's again wave theory, what it said, that only proved. So in that way, this becomes one of the limitations. Of Newton's corpuscular theory. And the remaining properties, just like interference, diffraction, and polarization, if you take, the remaining properties were not explained by this corpuscular theory. Right? So like that, there were some limitations. Then wave theory came out. And who propounded the wave theory? Do you have an idea? Do you have an idea who propounded wave theory? Yes? Yes? Lovely, dear. Some name you said, no? Ah, Maxwell. Okay, wave theory was proposed by Christian Huygens. Wave theory was proposed by Christian Huygens. And according to Huygens, light spreads in the space with the form of waves. According to Huygens, those waves are longitudinal by nature, remember. Very important points. According to Huygens, okay, so light waves are longitudinal by nature. Light waves are longitudinal. Light waves are longitudinal by nature. Okay, light waves are longitudinal by nature. Longitudinal by nature. Longitudinal by nature. Longitudinal by nature. But it is longitudinal. Longitudinal means all the medium particles will be vibrating parallel to the propagation of wave. That means, see this in this direction the light is propagating, and in front of this is medium particle. This medium particle vibrates like this. Medium particle vibrates like this, not like this. And if at all the particle vibrates perpendicular to the propagation, that becomes a transverse wave. So this is a longitudinal wave. But so therefore, longitudinal wave formation can be shown like this. This is the way how the longitudinal wave can be shown. Okay, so there are some places, okay, the particles are far apart, and which are called rarefactions. Rarefactions. So these are called rarefactions, and at some places, the medium particles come very close together. So they are known as compressions. They are known as compressions. Rarefactions and compressions. Rarefactions and compressions. Okay, so this is for the longitudinal wave propagation. Remember, everybody knows one thing. What is that? Medium is essential. For longitudinal wave propagation, medium is essential. So without medium, okay, the propagation of wave is not possible. Without medium, okay, propagation of longitudinal wave is possible. It's not possible. Okay, so if you take this Earth surface, this air is there. The air, okay, acts as medium for the propagation of light. And if you take space, means the distance between the sun and the Earth. The sun and the Earth. Okay, there will be some vacuum. There is no medium, no gases. Even then, sunlight is reaching the Earth. Not only sunlight, what about the stars present in the sky? Even the light coming from those stars is also reaching the Earth and the remaining planets. Are you getting my point? How does the propagation of light take place? Through vacuum. Even if vacuum is present in the space, how does the propagation of waves also take place? For that, what Huygens said, answer is, in this universe there is no vacuum. That's what he says. According to Huygens, in this universe there is no vacuum. There is no vacuum means there must be some matter, no? What should be that matter? The complete universe is spread, is pervaded by a highly elastic medium. That medium he named as ether. Ether medium is present. Ether means that is not something that you study in chemistry, organic chemistry. This is something different. Okay, so ether medium spreads all over. Okay, so this ether medium, okay, so this is having very low Young's modulus, very high rigidity modulus. Rigidity modulus. Rigidity modulus. Rigidity modulus sigma. Young's modulus Y. Capital Y means Young's modulus. Very low Young's modulus, very high rigidity modulus. very high rigidity modulus. Very low Young's modulus and very high rigidity modulus. Very high rigidity modulus. Understood? Okay, so that's what he gave, his explanation. And by means of that wave theory, by means of this wave theory, Huygens, okay, so look at this, by wave theory, Huygens, he could explain reflection properties successfully. Next, so even refraction he could explain successfully. Next, even interference he could explain successfully. Okay, and the fourth one is diffraction, so he could explain successfully. Understood? Okay, but the another property is there, polarization. Polarization he could not explain. Polarization he could not explain. By using this longitudinal wave nature, so polarization phenomenon could not be explained by Huygens. Okay, so that became the limitation of this Huygens wave theory. That became the limitation for this Huygens wave theory. Right? Next, in the late 18th century and beginning of 19th century. Okay, so there was a scientist, Max Planck. Okay, Maxwell, not Planck. Planck will come later. Okay, Maxwell. Okay, so Maxwell, he developed a new theory, that is electromagnetic wave theory. Electromagnetic waves were discovered by Maxwell. Electromagnetic wave theory in the beginning of 19th century. Okay, so according to Maxwell, electromagnetic waves, he propounded. The electromagnetic waves are radio waves, microwaves, so this is infrared waves like that. X-rays, all these things are different. Okay, radio, okay, this is electromagnetic waves of different frequencies, different wavelengths. Different frequencies and different wavelengths. Actually, Maxwell does not have any link with light. About light, he did not work out. Got it? Okay, so okay, so this is here, electromagnetic waves he was working out. Got it? So he identified, he explained, practically he showed how these electromagnetic waves can be produced. And according to him, what do you mean by electromagnetic wave? What do you mean by wave? In general, wave means that is nothing but disturbance that passes through a medium. Disturbance. Okay, whenever disturbance is created at any point of the medium, that disturbance will be passing in a particular direction. That is called a wave. Okay, now even for this electromagnetic wave, there must be some disturbance. What disturbance? That has to be electromagnetic disturbance, not mechanical disturbance. By means of mechanical disturbance, you will be getting so longitudinal waves, sound waves, water waves, this type of things. Electromagnetic disturbance means electric field has to be disturbed. Magnetic field has to be disturbed. The disturbance should be with respect to electric field and magnetic field. Where do we come across this electric field and magnetic field? From any charged particle. You take any charged particle, take electron. Okay, and if at all you look at electron, then the electron is moving. Okay, so electron basically a charged particle. Okay, by means of its own charge, electron will be exhibiting some field which is called electric field. When electron is accelerated, what happens? The field also changes. Sometimes it may be minimum, sometimes it may be maximum. And whatever the changes which take place in the electric field at a particular time. So, whatever the electric field linked with, so a charged particle, that is not constant. Then you may say, sorry, in the first chapter there is electric charges and fields. You told that, so electric field remains a constant. Yes, remaining, there's a here, it remains a constant. When there is a condition, the particle should not be in motion. The particle has to be stationary. When the particle is stationary, whatever the electric field it spreads, that remains stationary. That remains constant. But when the particle is moving, what happens then? Okay, whatever the electric field which is associated with this in the space, that electric field will be changing with the time. Sometimes it may increase, sometimes it may decrease, sometimes it may reach maximum, sometimes it may reach zero. So these many changes may happen, may take place in the electric field intensity. So all the changes are represented sinusoidally. Sinusoidally means there is a beautiful word, there is a terminology. Sinusoidally. Come on, tell. Sinusoidally we explain the changes. What do you mean by sinusoidally? What do you mean by sinusoidally? Amma? Sinusoidally means not change it. Whatever the changes which happen, all the changes are taken as a function of time. That function is nothing but sine function in trigonometry. Okay, sine function. It's a sine function. That is called sinusoidally. Sine function. Got it? So Maxwell he represented that in this way. So this is E naught sine omega t plus phi. So this is what the changes that happen, okay, in the electric field at any time. Here this E is the strength of electric field at a given time t. E naught is the maximum amplitude. Okay, so omega is angular frequency or angular velocity. Phi, that is a phase difference. That is the equation for electric field disturbance. Electric field disturbance or electric field wave. Electric field wave vector, anything we can call. It's a vector. Got it? Okay, and in the same way, so when electric field is there, okay, so this is here in electricity, last week, okay, so in Ramanasar's lectures you must have observed, wherever there is electric field, immediately magnetic field gets associated with that. That's what Oersted proposed. Oersted's observation was that when some amount of current passes, some amount of magnetic field gets linked with that. It's a natural phenomenon. You are not going to create. Remember, when some amount of electric current is passing, automatically some amount of magnetic field is associated with that. It's a natural process. It's a natural phenomenon. Okay, so along with this electric field, even magnetic field also will be there. Even this magnetic field also will be there. Okay, so this magnetic field which is B is equal to, so B naught sine omega t plus phi over here. B is equal to B naught sine omega t plus phi. Sine omega t plus phi. Sine omega t plus phi. So these two things represent electrical and magnetic disturbance. Ultimately, okay, so this disturbance will be passing like this. And if at all we take this as electric field vector, we can raise some. So this is electric field vector which is oscillating with this direction. Okay, so this is the maximum amplitude, maximum displacement of this oscillation of electric field. So this can be taken as E naught. This can be taken as E naught. E naught. Got it? Okay, so this is here, this is in this direction. This is in this direction. Say this is here. So if at all it is in the xy plane, right? Magnetic field will be perpendicular to that. Magnetic field will be so oscillating perpendicularly like this. So this is the way how the magnetic field oscillates. Magnetic field will be oscillating like this. This is magnetic field. So this is magnetic field like this. Like this. Okay, so this is okay. So whatever the maximum amplitude, this is called B naught. And ultimately both the waves together will be moving in a particular direction. Okay, so these two things are again perpendicular to the propagation of wave. So wave propagation will be in this direction. Okay, so wave propagation will be in this direction. So this is what electromagnetic wave. This is what electromagnetic wave. In electromagnetic wave, electric field vector, magnetic field vector, both things will be oscillating mutually perpendicular. Again, these two fields will be perpendicular to the propagation of the wave. To the propagation of the wave. To the propagation of the wave. Understood? To the propagation of the wave. To the propagation of the wave. Okay, actually Maxwell, he was working for this. Got it? So experimentally Maxwell, he found one thing. So what is that? The velocity of light Maxwell calculated. Okay, so velocity of electromagnetic waves according to Maxwell, okay, is 3 into 10 power 8 meter per second. Maxwell calculated the velocity of these electromagnetic waves as 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second. At the same time, during the same days, okay, not at the same place, at some other places of the world, there were two legendary physicists, two legendary scientists. Okay, so do you know who they are? Huh? Who are they? Two legendary scientists or physicists. Okay, they were Michelson and Morley. Michelson and Morley. Michelson and Morley. Very intelligent. And these two people, they were friends. Okay, these two people did many experiments for one sake. What is that? To find the velocity of light. Light, whatever the light that we have here, what is the speed of light? What is the speed of light? They conducted so many experiments. Got the point? Okay, so this is here. In this regard, so this there was one more scientist, he was Foucault. Foucault. He conducted an experiment which is rotating mirror experiments. Rotating mirror experiment he conducted. Rotating mirror experiments. Rotating mirror experiment he conducted. Foucault. Okay, Michelson and Morley, Foucault, all these experiments came to one conclusion. That light moves with the speed of the 3 into 10 power 8 meter per second. So this is the speed of light. This is the speed of light. So they found this value, they calculated the value and they published it. At the same time, Maxwell published the value. By seeing the same, similarity of these two values, Maxwell got an idea. Whatever the value I got, even these people also got the same value. How come it is possible? So light is not something else. Light is nothing but electromagnetic. Maxwell concluded by the similarity of these two values, Maxwell concluded that light is nothing but electromagnetic wave. Light is nothing but electromagnetic wave. Got the point? Okay, so when the light is electromagnetic wave, longitudinal nature should not be there because the electromagnetic waves obey transverse nature. The electromagnetic waves are transverse by nature. But what did Huygens say? What did Huygens say? Longitudinal wave. So light is not longitudinal wave. Light is electromagnetic wave which is transverse by nature. That's all. You see, in these many stages, the development has taken place. Okay, so by means of this Maxwell's electromagnetic wave, this Maxwell's electromagnetic wave gave jolt to many big theories. Got the point? Okay, so this before this fellow Maxwell. Okay, so that's here. So that's that Huygens, he was the hero. And whatever, the theory he propounded, all the people were discussing about that theory only. What is that? Light is, waves which are of longitudinal by nature. Longitudinal by nature. After Maxwell came, a big jolt has been given to the theory. What is that? Light is not longitudinal. Light is a transverse. Moreover, there is electromagnetic. And Maxwell, he told also one more thing. In the nature, in the universe, whatever the medium he predicted, either which is having very high rigidity modulus, very low Young's modulus, that type of material is not possible in fact. In the universe, you can't find any matter having very low Young's modulus, high rigidity modulus. High rigidity modulus. But okay, so the existence of either itself is inconsistent. Either medium is not there. Huygens told there is no vacuum. Maxwell says vacuum is there. In the space, in the universe. Okay, the electromagnetic waves don't require any medium. But okay, so whatever the sound waves which are longitudinal, whatever the water waves, okay, whatever, okay, the remaining waves, waves in the strings, wave in the, okay, air columns, they are mechanical waves. Means for the generation, for the production, for the manufacturing of those waves, initial energy, whatever we are supposed to give, that initial energy is nothing but mechanical energy. That will be in the form of either potential energy or kinetic energy. Either potential energy or kinetic energy. But electromagnetic waves is not a mechanical wave. It is electric and magnetic fields oscillations. They don't require medium. So electromagnetic waves can even pass through vacuum. Electromagnetic waves can even pass through vacuum. Can even pass through vacuum. In that way, light waves are able to pass through vacuum in the space. So that's what Maxwell proposed. Same theory gave jolt to another. Okay, that's a legendary theory also. Do you know what that is? One more legend was there. He propounded one more legendary theory. What is that? Rutherford's model of atom. Alpha is scatter action experiment. Even to that also, he kept a check. Got the point? Okay, so in Rutherford's model of atom, it was very successful. It was very brilliant. Rutherford's alpha scatter action experiment. In fact, that experiment was one of the milestone experiments in physics as well as chemistry. Both. Okay, so that's in chemistry we study, in physics also we study. Rutherford's alpha scatter action experiments. Got the point? Okay, that type of legendary theory has got one limitation. That is due to this fellow, Maxwell. Understood? Understood? Okay, that's why Niels Bohr had to come, okay, into picture. Actually, Niels Bohr, he was the assistant of Rutherford. Niels Bohr, he used to work in Rutherford's lab. Rutherford, he used to have his own lab. In that lab, Niels Bohr, he used to work. Okay, Niels Bohr propounded one more theory, which is there's a Niels Bohr's model of atom. Okay, so this Niels Bohr, he was very scholastic, he propounded the model of atom. Even then, some more limitations came. Then Sommerfeld came forward. Sommerfeld. Okay, so this here, there's a Rutherford propounded circular orbits. Niels Bohr also propounded circular orbits, whereas Sommerfeld propounded elliptical orbits. By means of elliptical orbits inside the atom around the nucleus, okay, so all limitations were rectified. Whatever the limitations that we came across in all the previous models of atom, all those limitations were explained successfully by Sommerfeld by introducing quantum numbers. By introducing quantum numbers. In chemistry, you must have studied 4 quantum numbers. Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Okay, so that's here. All these quantum numbers were, okay, so that's explained by Sommerfeld. Of course, each and every quantum number was proposed by some, okay, particular scientist. But that time, by means by, okay, combining, by governing all these quantum numbers, he propounded the model of this atom, Sommerfeld. Understood? Okay, that will also in atoms chapter we will discuss. The term that's given the track that's ionability. Got it? Okay. Now this is something about the brief okay introduction of light and its propagation. Light and its propagation. Now is it clear? Is it clear? Okay. So in my lecture, whatever the thing that comes out of my mouth, each and everything is very, very important. I'm telling you. Got it? I am telling you. Okay, and each and everything is getting recorded, and whenever you have a leisure time, okay, so that's here you can, okay, that's you have your phones, but the point is, phones are not there with you, not allowed, permission is not given, but they are using now, Neet people, repeaters, permission is there for them, but for you permission is not there. Huh? Okay, so that's if possible, you get the permission from principal sir. Okay, so if your phones are allowed to you, okay, so that's here, all these lectures that you can access. Not find all these lectures. Okay, so at night, okay, this you can go through. Understood? That is right. Okay, what I'm telling you is this is okay a brief introduction of this light and its propagation. Right? Now coming to the next thing. Properties, we were discussing now, properties. Properties. Okay, so what do you mean by properties over here? Light exhibits some of the properties. Light exhibits some of the properties. So properties of light. The very first one is rectilinear propagation. The very first one is rectilinear propagation. Rectilinear propagation. Okay. So next, the second one is reflection is another property, and the third one is refraction is another property, and the fourth one is interference is another property, and the fifth one is diffraction. So diffraction is another property. And the sixth one is polarization. Polarization. So these are the main properties. These are the main properties. Okay, so in these three properties, there's six properties. So the first three properties, if you take, these three properties are explained by ray properties. And the remaining three properties, if you take, these are explained by wave properties. In the ray optics, our complete discussion will be rectilinear propagation, reflection, diffraction. That's all. By refraction, ray optics will get over. Okay, in the wave optics, we will come across this interference, diffraction, polarization. That's all. In the complete wave optics chapter, so you will see only these three things. You will see only those three things. Understood? Okay, so this is something about the categorization. This is something about the categorization. Now, about each and every property we need to discuss. So, the very first one is rectilinear propagation. The very first one is rectilinear propagation of light. The very first one is rectilinear propagation. Rectilinear propagation. Rectilinear propagation. So, what do you mean by rectilinear propagation? Straight line propagation of light from the source in the space. Okay, so from the source, the light will be moving in the form of straight lines. In the form of straight lines, the light propagation takes place. That is called rectilinear propagation. So, what is the consequence of this rectilinear propagation? What do we get? Tell me. What is the consequence of this rectilinear propagation? By means of this rectilinear propagation, what do we get? That is called a consequence. Yes. Yes, Sagar, you are telling something. By means of this rectilinear propagation, what is the consequence? What do we get? What do we get? Silence. Silence. What is the consequence? See here. Okay, so I am placing this body over here like this. And because of rectilinear propagation, okay, so if the light is propagating over here like this, okay, so for that light, this becomes an obstacle. Okay, some obstacle has come here. So what do we have to do now? Okay, take right on, yes, come on, left on, yes. Okay, then pass. Is the right pass like that? Is the right pass like that? No. When the obstacle comes, okay, in its path, light will not travel, that's all. Then it is opaque. When it is transparent, it passes through. Got it? Okay, when it is opaque, finish. The light cannot pass. Rectilinear propagation. Rectilinear propagation. So by means of this, okay, so this, all these light rays cannot pass through. Therefore, here what is getting formed? Shadow. Shadow formation is the consequence of rectilinear propagation. Shadow formation is nothing but consequence of rectilinear propagation. Rectilinear propagation. And you may ask, what advantages, what benefits do we get by means of shadows? What benefits do we get? By means of shadows formation, only eclipses take place. Okay, like this. Solar eclipse, lunar eclipse. What is that? What is that? Okay, solar eclipse. Solar eclipse means, so whose shadow is getting formed on the earth? Moon's shadow. Therefore, sun is behind. Moon comes in between. So, if that shadowed region, people will not be able to see the sun. That becomes a solar eclipse. Are you getting my point? That becomes a solar eclipse. What is it? Okay, so this is here, shadow. And because of the shadow formation only, eclipses happen in the nature. Eclipses happen in the nature. Got it? Okay, so that is due to rectilinear propagation. That is due to rectilinear propagation. One more thing also happens. That is diffraction. Okay, when we come to diffraction, okay, concept then I will tell. By means of rectilinear propagation, one region gets formed due to this during the eclipse formation. What is that? Umbra region. Due to diffraction, so one more region gets formed during eclipses. That is penumbra. Umbra and penumbra. So didn't you hear these words? Huh? Oh man? Huh? So look at this. This is the sun. This is the earth. Okay, so during its the revolution around the earth. Okay, so moon will come. Sun, moon, earth, all the three things will come on the straight line. When all these three things come on straight line, what happens? Okay, the sun's rays will be passing like this. Okay, so the sun's rays will be reaching over here like this. Okay, so during this sun's rays will not touch. So, okay, the people of this area, okay, will not be able to see the sun completely. That is a complete solar eclipse. Complete solar eclipse. Okay, but because of diffraction, what happens? What about the light rays which are passing over here like this? Okay, so the light rays undergo diffraction effect. These light rays undergo diffraction effect. Even these people, these areas, these regions on the globe, on the earth, also so experience solar eclipse. Okay, this is partial. This is umbra region. These two are penumbra regions. Umbra region means a perfect shadow. Those people will not be able to see. That is a total solar eclipse. At least, did you ever hear this word? Okay, this is in Karnataka area. Total solar eclipse, total lunar eclipse. Have you heard of this? Partial. Partial means, that means we are in penumbra region. Okay, total solar eclipse means we are in umbra region. We are in umbra region. Got it like this? Okay, umbra region is because of rectilinear propagation. Penumbra during the eclipse formation is because of diffraction. Because of diffraction. Okay, so by means of this, okay, so this is the thing that we need to notice. Right, now coming to the next thing out here. Coming to the next thing, reflection of light. So this is what we notice. Okay, so reflection of light. So what do you mean by reflection? What do you mean by reflection? You tell. What do you mean by reflection? Reflection is a phenomenon in which light ray undergoes bouncing nature. Okay, so whenever the light ray is incident, incident means is sent. Incident means is touched. Is sent, is passed. Anything you can say. Right? So here you see this is the source of light. You see the light ray is passing like this way. This is the way how the light ray passes. Okay, the moment the light hits this surface, what happens then? So the light ray undergoes a kind of bouncing back nature. The bouncing back nature that takes place in the case of light ray, that is known as a reflection. The light which is moving, so this is the point where the light ray is touching. So this is called point of incidence, we call it. This is called point of incidence, we call it. Okay, so S2O. So the light ray is known as incident ray. So we call it. This is called incident ray. This is called incident ray. Incident ray. Okay, next O, and this is S dash. You take okay, O to S dash. This is called a reflected ray. So this is called a reflected ray. Now to measure, okay, angles, we need one thing. What is that? Normal. Normal means perpendicular. Okay, so we need to draw a normal or perpendicular, okay, to the reflecting surface. So this is the normal drawn. This is the normal, that is N, O, N dash. N, O, N dash. There is a normal drawn through the point of incidence to the reflecting surface. Okay, so this is a reflecting surface. This is a reflecting surface. This is a reflecting surface. The angle between the incident ray to the normal, this is called the angle of incidence. The angle between the normal to the reflected ray, that is called the angle of reflection. That is called the angle of reflection. That is called the angle of reflection. Understood? Okay. Now coming to the next thing over here. So that's here. One more angle. Okay, this will be come across. In fact, when the light ray is incident on any surface, normal you have to imagine. Normal will not be present over there. You need to draw. Okay, so look at this here. You see. So this is a surface I have taken. Light ray is incident like this. And immediately, what is the angle that I see? What is the angle that I see? This is the angle that I see. Am I correct? Not okay, normal, okay, so the angle between the, okay, incident ray to the normal. This, if at all you want to see this, you need to imagine where the normal is. But is the normal present over there? No. So immediately, what is the angle that we see? The angle between the reflecting surface to the, so this is the incident. What do we call this angle? That is called the angle of glancing. What's the name? Sagar forgot. The angle of glancing. Even this thing also is angle of glancing. Even this thing is angle of glancing. The angle of glancing. Okay, now there's a loss of reflection. So this is what we can see over here. So loss of reflection. Loss of reflection. Loss of reflection. Okay, so what are the loss of reflection? What are the loss of reflection over here? Okay, so there are two losses. One is incident ray, normal, and reflected ray. All the three things lie in the same plane. Okay, and the second law is the angle of incidence is equal to the angle of reflection. The angle of incidence is equal to the angle of reflection. That is the second law. But remember, this second law does not hold good every time. If at all the second law holds good, means there must be some condition. What is the condition? This type of thing happens only when the reflecting surface is very, very smooth and polished. So then only this condition holds. Otherwise, okay, I is not equal to R. And whenever, okay, so the angle of incidence is equal to the angle of reflection, what happens? What is the consequence? Image formation, okay, takes place. So images are formed. Images are formed. Images are formed. This type of reflection is known as regular reflection, we call. This type of reflection is known as a regular reflection. Regular reflection. Regular reflection. We call this one as a regular reflection. Regular reflection. Understood? Okay. Now, so there's whenever the reflecting surface is okay, rough and uneven. Okay, so rough and uneven. Rough and uneven. Now then what happens? The things will get this. So this is the reflecting surface. When this is and this is incident ray, so reflected ray will be like this. And if you draw a normal, so this becomes the angle of incidence, this becomes the angle of reflection. So in this case, the angle of incidence is not equal to the angle of reflection. Okay, so what do we call this type of reflection? So this is called so irregular reflection we call. Okay, so this is also known as a diffuse reflection also. Diffuse reflection. Okay, so here, this type of diffuse reflection only causes scatter action of light. One more property. Understood? Scatter action. Got it? Okay, scatter action in the sense immediately. So this who was a scientist that you have to remember. Yes, scatter action immediately. This here. So which scientist has to come here? Amma? Tell loudly. Wonderful. Sir C.V. Raman. Sir C.V. Raman, our Indian physicist. The Nobel Prize laureate. Okay, so he explained the back scatter action of light. Okay, that's from the sky. Okay, after Sir C.V. Raman's theory, how the sky appears blue in color during midday, how sky appears yellowish, reddish, orangish. Okay, at the time of sunset, at the time of sunrise, all the things we can explain by means of back scatter action of light. Back scatter action of light. Sir C.V. Raman. Understood? Scatter action of light. And we have so many devices. Why Nobel Prize was given? Because what about the scatter action of light? Sir C.V. Raman explained, we made some devices. By means of those devices, we have so many applications. You see, so for any physics theory, if at all you are given, okay, Nobel Prize, what is the condition? Your theory may be very great, so great. But, okay, the greatness behind the theory, that's what they don't see. And what about the theory that you are developing in physics or chemistry, whatever it may be, how far it is useful to the mankind, to the society? How can you develop a society? That's what they see. Okay, so Einstein you take. Einstein, in 1905 only he became legend. Okay, so this are all scientists of this all over the world, they could not come up to the level of Einstein. What he was telling, so many people could not understand. Why? Theory of relativity. 3 papers he performed at the age of 21. At the age of, there's 18 to 20 years boy, 21. Got it? Okay, legend. So by the time he became legend. Everywhere, Einstein's name was echoing like anything. But for that theory of relativity, next, special theory of relativity, this he explained. By means of these two theories, okay, complete universe he explained. Universe alignment. By means of these two theories, Einstein, he challenged Newtonian mechanics. Okay, he challenged Newtonian mechanics. Okay, there's the mechanics he developed. But the point, okay, the theory was a legendary theory. But the people felt that, okay, society will not get benefited by means of that. Theory was very great. Then what is the use of society? What is the use of the theory to the society? So he was not given Nobel Prize. He was given Nobel Prize in 1921 for photoelectric effect. Because it has got practical utilities. Photoelectric effect. Understood? But so before that, actually, when you compare the greatness of the two theories, the theory of relativity and photoelectric effect is a small child. A small child before that legendary theory of relativity. Got it? But for that small theory, he got Nobel Prize. For the small theory, he got Nobel Prize. Are you getting my point? Okay. And so coming to this, Madame Curie, she was, still more powerful legend. Even including Einstein. Einstein, we admire of his, way of thinking, way of, there's a here, giving the ideas and other things. But the type of Einstein also got only once. But Madame Curie, 2 times she was given Nobel Prize. Once for physics, once for chemistry. Madame Curie. Madame Curie. Because whatever the things Madame Curie did, each and everything is applicable to the society. Today, for cancer treatment, we are using radiology, other things just because of Madame Curie's work. Are you getting my point? So, radioactivity we are using in the industries just because of, Madame Curie's work. Radioactivity we are using in producing electricity just because of Madame Curie's work. But so that and all they see to give Nobel Prize. Understood? Okay, so this what I'm doing is here you see. Okay, so that's here. So irregular reflection or diffuse reflection, even scatter action is one of the applications of that diffuse reflection. Scatter action is one of the applications of this diffuse reflection or irregular reflection. So what is the consequence of this irregular reflection? Tell. What is the consequence? What is the consequence? By means of regular reflection, we are getting images. Image formation can be taken as a consequence of regular. What is the consequence of irregular reflection? Tell. Tell me. Sense of vision. Sense of vision. Sense of vision takes place. Sense of vision takes place by means of this irregular reflection. Images will not get formed. Images will not get formed. When images are not formed, what will happen? What will happen? Sense of vision occurs. Means we will be able to see the bodies. We will be able to see the bodies by means of this sense of vision. By means of this sense of vision. But again, like this. So this is something about reflection. Now, so reflection, so I told you that, in the regular reflection, images are formed. Now our focus will be that. Now our focus will be that. So regular, so reflection, image formation. So we will be taking 2 different types of surfaces. One is a plane surface. The second one is a curved surface. Reflection by a plane mirror. Reflection by a plane mirror. Reflection by plane mirror. So we may have some problems based on this reflection. By plane mirrors. We have some problems based on this. We have some problems based on this. Reflection by a plane mirror. So look at this plane mirror I am taking over here like this. So this is a transparent glass plate. So when the glass plate is transparent, what happens? The reflection will not take place. Means this here, the white light will undergo refraction. Of course, some slight reflection will take place, but there is very 5% to 10%. 90 to 95% of light undergoes refraction when it is transparent. Now if at all you want to make this as a mirror, so silver coating has to be applied. This is the silver coating. This is the silver coating. Silver coating has to be applied. Silver coating. That silver AG, same silver. That AG coating, silver coating has to be applied. Then the silver, prevents the refraction. The silver makes light undergo reflection perfectly. Then it becomes a mirror. Then it becomes a mirror. I will be taking one object over here. This is the object. Observer is present over here. If observer is present over here, so what about the light rays which are coming directly? The observer will be getting. That is a direct vision. Direct vision. So if at all observer sees this object into the mirror also object will be seen. So how does that mechanism take place over here? This is observer's eye. This is observer's eye. Okay, so whatever the light ray which is incident over here like this light ray undergoes reflection like this. This reflected light ray will pass. Okay, through the observer's eye. Next, like this, how many light rays will be coming from object? Only one light ray. Yes, okay, through here. No, an infinite number of light rays will be coming out. Okay, so this here one more light ray. This will be passing over here like this. Even this light ray undergoes reflection like this. And all these things are regular reflections. All these things are regular reflections. Even this light ray undergoes in the same angle. Okay, so this again, if you take normal over here, the angle of incidence is equal to the angle of reflection. You take normal over here, the angle of incidence is equal to the angle of reflection. You take it. So normal over here, the angle of incidence is equal to the angle of reflection. Okay, so from the surface, all these light rays are coming back, moving back. But for the observer, okay, so this type of bending of the light rays, so that and all observer will not be able to see. For observer, only one thing will be seen. What is that? So since this light ray is coming like this light ray's actual origin is somewhere over here. This light ray's actual origin is somewhere over here like this. Even this light ray's actual origin is somewhere over here like this. Okay, observer feels that this object is here. So this is dash. Understood? Okay, so this dash becomes the image of this object. Dash becomes image for this object. Okay, so then this is object that we have taken. So this becomes the image over here. This becomes the image. Okay, so there are some important characteristics that you need to keep in mind for this image formation. And what is that? This object and image. So both the things lie on the same plane. And one more thing. So this object distance from the mirror will be equal to image distance from the mirror. Okay, so image is formed as far behind the mirror as the object is before the mirror. Try to get my language. Once again, I repeat. Image is formed as far behind the mirror as the object is before the mirror. As the object is in front of the mirror. Are you clear with this point? Same point. You need to remember. Okay, and one more thing. The size of the image and the size of the object both of these are equal. In the case of plane mirror. Small image, big image, same. This type of variations we come across in the spectrograms. But in the case of plane mirror, always the same size image will get formed. Okay, so the size of the image is equal to the size of the object. The size of the image is equal to the size of the object. The size of the object. The size of the object. Got it? And one more thing. See here. What is that? What do we call? See, the moment power comes to tap, heavily it starts rotating. Now it is picking up. What do we call that heaviness? Inertia. Moment of inertia. Rotational inertia. Okay, that we discussed in the first year. Since the example is being shown, exhibited, immediately there's I do. This is called moment of inertia. Because till then the fan was at rest. The moment power comes, the fan, so this is trying to rotate, but the fan is reluctant. He is not willing to rotate. It wants to be in the same state of rest. But whatever the electricity which is entering, that electricity will not keep quiet. That electricity will be rotating the motor. Are you getting my point? That is called moment of inertia. I is equal to mr square formula. I is equal to mr square. Okay, now let's come back to this. Present discussion. Okay, now the size of the image is equal to size of the object. Okay, and one more important characteristic that we have to keep in mind is object is so that image is laterally inverted. Okay, lateral inversion takes place. Lateral inversion takes place. Laterally inverted. Laterally inverted. Laterally inverted. Laterally inverted. So what do you mean by lateral inversion? Lateral inversion in the sense that the left part of the object seems to be right in the image. The right part of the object seems to be left in the image. Okay, so this you can, practically experience when you stand before the mirror. Okay, plain mirror, that is a dressing table. But it, and if at all, this you get anything that's over here, you just plot, try to plot this in that particular you cannot. If you put here, your finger will be going this side. Did you ever notice? Did you ever notice? And because of lateral inversion. Because of lateral inversion. Okay, so the complete left portion of your body appears to be right in the image. The complete right portion of the body appears to be left in the image. That is called lateral inversion. And what is the practical, just the usage, what is the practical application of this lateral inversion? Where do we see? Yes. Where do we see this practical? Okay, so this application, where do we get? This lateral inversion, where do we get? Where do we get? Huh? What are you? Silence, sir? Huh? Huh? What? Where do we see the practical application of this lateral inversion? Ambulance. Ambulance. On the front part of the ambulance, how is? Okay, it's written. Okay. Okay. Like this. Like this it is written. Ambulance. Did you ever notice? Okay, why is it written like this? Mirror image. Mirror image formation. Okay, so ambulance means that is a vehicle which has to meet emergency. Yes or no? Okay, inside the vehicle there will be some fellow, there's a who booked the ticket. Reservation. Reservation is booked for the fellow. Yes or no? The reservation is booked. Like that is the fellow will be. Yes or no? Okay, in such cases, so this is slowly, on the way having some cup of tea, and so this is like that, he goes like that. Yes or no? Okay, so his ticket is, so conformly conformed. Yes or no? Okay, that means the fellow is RAC, reservation against cancellation. So this train ticket, sometimes RAC we will get no. RAC like that, okay, so the RAC booked fellow will be there, behind the vehicle, in the vehicle. Yes or no? So the driver has to take the vehicle as early as possible, then only the RAC will be cancelled. Otherwise, RAC will be confirmed. RAC will be confirmed. Waiting list. Got it? Okay. So this is in such cases, the vehicle which is before the ambulance, that driver will see this through his rear view mirror. Okay. When the lettering is like this, immediately that will be written. This that will be seen. So in the normal way. Then immediately that's the driver will be able to read. Then this ambulance, he will move aside, he will give the way. But sometimes, so this, there will be some illiterate drivers. So even if the ambulance, they will not be able to see the rear spinning. That's why that horn and sound and all the things they make. But so ambulance, is going. So there's the horns and all the things too. So this will make the people to make the people aware of. Some emergency. That's why for ambulance, no traffic rules. Do you know that? Even if the red light, red stop light is given, ambulance can go. Even if the traffic jam is there, even the wrong route also, there's an ambulance can go. Even the wrong routes. So even the right side also ambulance can go. Got the mind? So like this. So this is the application, the practical application of the lateral inversion. Now in this reflection by this, here you see. So what about the image that is getting formed here? So look at this, here you see. So this light ray I have shown as a solid line. These light rays I have shown as dotted lines. And what is the difference between these two things? Solid light means there is an actual light. The actual light ray is that. But this is not the actual light ray. This is the light rays which are, okay, seen by the observer. Means apparent. Means virtual. They seem to be passing. They appear to be passing. But the actual light ray will not be there. The actual light ray will not be there. Okay, sometimes we will be getting the images by the intersection of these real light rays. Whenever the image gets formed out of this, the intersection of these real light rays, then that is called real image. Real image. Real image. A real image is the image which is formed by the intersection of real light rays. Existing light rays. Got the point? Okay, that is called real image. Okay, so if at all image is formed out of this type of imaginary light rays, imaginary, where the light rays are not present over there physically. Got it? So these are called imaginary light rays. These are called imaginary light rays. By means of these virtual light rays, whenever the image gets formed, it is called virtual image, we say. That is called virtual image, we say. A real image and virtual image. A real image and virtual image. A real image and virtual image. Right? Okay, so what is the main difference that we come across in between this real image and virtual image? See, real image is always, yes, real image means there is inverted only. That's all. You can, okay, come to conclusion. Never real image is erect, upright, upright. Right? Okay, so this virtual image is always, okay, so this here, okay, this upright. Always erect. Always erect. Erect means upright. 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 Understood? Okay, coming to smaller, bigger, same size, in both the images, all the three things are happening. Real images, smaller images are there. Real images, bigger images are there. Real images, same size images are there. And even the same way, so even in the virtual images also, okay, smaller ones are there, bigger ones are there, same sizes are there. Are you getting my point? Okay, so with respect to size of image, you can't distinguish. And one more, okay, there's here very, okay, prominent difference we can tell in both the images. What is that? Real image can be caught on the screen. On the screen means, so this is different with the screen. Okay, the real image is getting formed on the screen, that's what you can catch and you can see that. But okay, so this is here, inverted image will be seen. Inverted image will be seen. And if at all you put, okay, so a concave mirror, you take a concave mirror, okay, so there's here, there are some people going on, so going there, okay, and this you put a concave mirror over here, and you put the screen over here, you can catch the image of that person on the screen. Okay, upside down, inverted. Inverted person will be walking over here. Got it? Okay, whereas, okay, virtual image. Virtual image means that can be seen, but that cannot be caught. That can be seen, but that cannot be caught. And if at all you stand before, okay, this is here, your dressing table, okay, so this is your face, this is your, okay, that's the body will be visible. Okay, so where is my body? Can you touch? Can you touch your image? Tell? You can't, but you can see. You can see, but you can't touch. Got it? Okay, so like this. So that can be taken as a prominent difference. There are two prominent differences that we can give for real image and virtual image. The first prominent difference, universal difference, what is that? Real images can be caught on the screen, okay, but virtual images cannot be caught. They can be just seen. The second prominent difference that we can give for these two images is real images are always inverted, upside down. Upside down. But mind, whereas virtual images are always erect. Understand? Okay, like this. Okay, so this is something about this. Now, so I will be taking another important concepts based on which we have problems based on which we have problems. What is that? Deviation, angle of deviation. Angle of deviation. Angle of deviation. So what do you mean by angle of deviation? This is what we have to look now. What do you mean by angle of deviation? Now look at this here, you see. So I will be taking one plane mirror over here. I will be taking one plane mirror over here. Yes. Okay. So I will take the source of light. The light ray is passing like this. The light ray is passing like this. Okay. So the light ray undergoes reflection over here. For the sake of the angle of incidence, the angle of reflection, you will be drawing one normal. This is the point of incidence O. Okay, this is N, O, N dash becomes a normal. O, S dash becomes a reflected ray. S, O becomes an incident ray. Okay, now this is angle of incidence I. This becomes the angle of reflection R. Okay, so the second law of reflection says that the angle of incidence is equal to the angle of reflection because this is the reflection by smooth surface, mirror. So, regular reflection only takes place. So, regular reflection only takes place. Okay, I is equal to R. I is equal to R. So, that is equal to theta. Say. Both are same. Both are same. Okay, so what is the angle of deviation? Angle of deviation means from the usual propagation of the incident ray, the final ray, at what angle it is getting deviated. So what is the usual propagation? If at all this surface is not there, so along what path this light ray is supposed to travel? The light ray is supposed to travel like this. Yes or no? From this usual propagation, the light ray undergoes a deviation or bending like this. So this is called the angle of deviation, delta. Delta symbol. Delta symbol. That is angle of deviation. The angle of deviation. Okay. So the angle of deviation, what is that? So this total angle is how much? 180 degrees. Okay. So that's again you see. So I plus R plus angle of deviation is equal to 180 degrees. Okay, I is equal to R is equal to theta. I said theta plus delta is equal to 180 degrees. Okay, so this is 2 theta plus delta is equal to 180 degrees. Therefore, delta is equal to 180 minus 2 theta. So this is the formula that we use for the angle of deviation. This is the formula that we use for the angle of deviation. The angle of deviation. Okay. Now, in this particular case, we will be taking somewhat advanced level. Okay, so what is that? The total angle of reflection, the total angle of deviation when the light ray undergoes multiple reflections. Multiple reflections means, okay, that is not possible by means of a single mirror. Okay, 2-3 mirrors we have to take, 2-3 mirrors of combination we have to take. Yes or no? So what I do is, I will be just taking over here, look at this, here you see. So one mirror I am taking over here. This is a mirror, okay, plane mirror. This is one plane mirror, M1 I am taking. I will be just placing one more plane mirror over here. I will be just taking one more plane mirror over here. So this is M2 over here. There is an angle between the two plane mirrors of theta. Now what happens is I will be just taking one light ray over here like this. Let this light ray be incident with some angle alpha, you say. Okay. Now what happens then? The light ray undergoes reflection. In what way? So the light ray undergoes reflection over here like this. The light ray, okay, undergoes reflection like this. Understood? Okay, and if you draw one more perpendicular over here like this, so this becomes beta, you say. Beta, you say. Got it? Beta, you say. Now, you need to represent, you need to calculate the total, okay, angle of reflection. Total angle of reflection. By means of this, I will tell you one thing. Okay, one practical difficulty I will show by these arts. One practical difficulty I will show you. Anyone here? Okay, one practical difficulty I will show you. Okay, first you find out this. So total angle of deviation you need to calculate. Delta is how much? Delta is how much? Come on, please make it fast. Time is not there. Yes, come on. This much time you should got it. Fatafat. Just geometry. Okay, so this is 99% problems of this ray optics are solved out of geometry. That's why ray optics is also known as geometric optics. Ray optics is also known as geometric optics. Why? Because by establishing geometry we will be solving each and every one. Same geometry that's what we will be using over here. Same geometry we will be using over here. Yes, calculator. 360 minus 2 theta, she says. 360 minus 2 theta. What's that? Sachin, Akhilesh, Mayur, alpha into beta. 360 minus 2 into alpha plus beta. Yes. Next, any more? Any more? Okay, so look at this. I will work out. Okay. So both of these are correct, but you are halfway. She has completed. You are halfway. Still, okay, something else which has to be done. That you will not do. They completed. Okay, so this, I will show you how it is. Look at this, the given situation is like this. So let's here how we have to take up this approach. This you can understand. Okay, so this is the mirror M1, and I will be taking, okay, there's one more mirror over here like this. One more mirror over here like this. This is the mirror M1. Okay, so there is an angle between the two things, that is a theta. Right? In this regard, one sign convention we need to apply. Okay, sign convention. sign convention you need to take. So what is the sign convention over here? Whenever angle of deviation is found to be in the anti-clockwise direction. Okay, so the angle of deviation delta is in the anti-clockwise direction. Okay, anti-clockwise direction. Take that angle of deviation as positive. Just like our mechanics. Even mechanics, okay, the angle in the anti-clockwise direction we take as positive. The angle in the clockwise direction we take as negative. Same sign convention we apply. So the angle of deviation, so which is in the clockwise direction. So which is in the clockwise direction is taken as negative. Clockwise direction is taken as negative. Clockwise direction as negative. Okay, so this sign convention we will be applying over here, right? Now look at this over here, what's happening? So look at this, here you see, a light ray is incident at a particular angle of incidence. So this is alpha. Then the light ray undergoes reflection, right? So after reflection, how will the light ray pass? The light ray will be passing over like this. Okay, then this is the angle of incidence which is alpha. What will be the angle of reflection? Simple alpha. And what will be the usual propagation of light ray? This is the usual propagation of incident ray. From this usual propagation, the light ray is getting deviated. This is the first deviation, delta 1. And what do you say this delta 1 over here? Delta 1 is equal to 180 minus 2 alpha. Delta 1 is taken as 180 minus 2 alpha. 180 minus 2 alpha. Okay, so what will be the direction? Is it clockwise or anti-clockwise? Clockwise. So this is taken as negative. Okay, so delta 1 I will be taking as negative. Negative. Delta 1 I am taking as negative. Okay, so with this negative, so how do you take this? Delta 1 is equal to, so 2 alpha minus 180, like this you write. Okay, now, so light ray undergoes a reflection over here. This is the reflected ray. For the second mirror M2, this reflected ray becomes the incident ray. Now, the second reflection is taking place from the second mirror. Okay, so from the second mirror, light ray undergoes reflection over here. Okay, now, this is the normal drawn to this, and the angle of incidence beta is taken. Then the angle of reflection is also beta. And what is the actual propagation of this incident ray? Like this. Okay, the actual propagation of light ray is like this. Understand? So from this usual propagation, light ray is undergoing. Okay, and this is the delta 2. And how do you write delta 2 over here? Delta 2 is equal to 180 minus 2 beta. Now you tell, is this delta 2 positive or negative? Negative. Because even this thing also is found in the clockwise direction. Okay, so even this thing also is negative over here. So delta 2 is equal to 2 beta minus 180. Now, what is the total deviation? What is the total deviation over here? Okay, so total deviation. Total deviation. Total deviation. Total deviation. Okay, so total deviation. What is the total deviation? So delta is equal to delta 1 plus delta 1 plus delta 2. Okay, so delta is equal to so delta 1 2 alpha minus 180. Okay, plus 2 beta minus 180. So delta is equal to, what do you say? So 2 into alpha plus beta minus 360. Understood? Okay. So I will write like this, minus 360 minus 2 into alpha plus beta. Okay. So this is here, alpha plus beta. Look at this. When this is alpha, this will be what? 90 minus alpha. Okay, this is normal. From here to here, 90. When this is beta, this becomes 90 minus beta. Okay, now, so the angle sum property of triangles I will apply. Theta plus 90 minus alpha plus 90 minus beta should be equal to 180 minus 90 plus 90, 180. Okay, so theta minus so this is alpha plus beta is equal to 0. Therefore, alpha plus beta is equal to theta. Okay, so delta total. Okay, so 360 minus 2 theta. So negative means okay, it is in the clockwise direction. Clockwise direction. It is in the clockwise direction. It is in the clockwise direction. Okay. Now I told you one thing. One practical difficulty I will explain. Okay, this is the brightness of this. First, you note it down this one. You note it down this one. Yes. Okay. Now I will give one problem. That problem through this formula. This we can use as formula. 360 minus 2 theta. What about the equation that we got? That will become formula. Direct formula we cannot. I will give you one situation. Okay. So that situation in two ways we will do. Out of this discussion we will do. Out of formula we will do. And both the things have to be same now. Yes or no? When this formula is universally correct, okay, so this formula has to give the solution, okay, everywhere. Can I have? Okay, we will see. Over this one? Okay, now I will give you one situation. I will give you one situation. That situation, in both the ways, we will discuss. I will be giving one mirror over here. I will be giving one more mirror over here like this. The angle between the two mirrors is 30 degrees I am giving. I will be taking one light ray which is incident over here at an angle of 45 degrees. Calculate the total angle of deviation. First, by using formula you do. You tell by using formula first. First, by using formula you tell how much? How much? 300 degrees. Okay. So, by using this formula, we have 300 degrees. Okay. Correct. By discussion. By discussion. By discussion, you also find out. Are you getting the same answer or different answer? How much? 60. How much? Plus 60. Okay. So he says plus 60. How much? But both are different now. Both are different. Now, which one is correct? Is 300 correct or 60 degrees is correct? And what about the formula that we derived over here? Out of derivation it came. So you should not have any suspicions. You should not have any confusion with that. That formula is also correct. But the formula is giving you 300 degrees. And what about the analytical method that you took up now? The analysis gives you 60 degrees. That is a practical difficulty, practical problem. Why? Where does that practical difficulty lie? Can you identify? Can you identify? Okay, so look at this. In this particular case, you work it out now. By means of your workout, this you have to come to know immediately. Here there is a twist. The twist you might have seen, but you were not telling. Sir, here, sir, in this area, twist is there. Because of this, we are not getting. Already you did it. And whatever 60 that you know, that is correct. I appreciate it. Whatever 60 you told, that is absolutely correct. I appreciate it. But where the twist is hidden? What English? Look at this. Okay, this discussion I will take up. Right? Now, this 45 degrees is the angle of incidence. Okay, first by formula. So the total deviation is 360 minus 2 theta. So 360 minus theta is the angle between the two mirrors. Okay, that is 300 degrees. It has to be like this. Okay, now, there's an analytical approach we will take. Now look at this. This is incident ray. 45 degrees is the angle of incidence. Now, during this reflection, what happens? So the light ray undergoes reflection of the lights. The light ray undergoes reflection of the lights. Okay? So this thing also is fine. And if at all you extend this light ray, this is usual propagation. Okay, so this is the first angle of deviation which is in the clockwise direction. Delta 1 is good negative. So 180 minus 2 theta. 180 minus 2 into 45. Are you clear with this? Okay. Now let us come to second reflection. Okay. So during the second reflection, so look at this here. For this plane mirror, you need to draw normal. You need to draw perpendicular. Perpendicular means 90 degrees. And first of all, see the angle. See, when this is 45, what will be this angle? 45. This is 45, this is 30. What should be the angle over here? 1. Now you are drawing perpendicular. Perpendicular means, look at this. This is a perpendicular. So the angle between this is 90 degrees. If you draw perpendicular, now you tell normal will it lie this side of this light ray or this side of the light ray? This side. Be clear with this point. Okay. So the total angle is 105. So 90 degrees line you are drawing. Usually the 90 degrees line will be this side. Am I correct? So this is 90. Yes or no? Okay, now in this particular case, what's happening? That incident ray lies that side of the normal, not this side. That side is the normal. Okay, now this becomes the angle of the incidence. How much? 4 9 is 105. From here to here 90. So this is 15 degrees. 15 degrees is the angle of incidence. Understood? Okay, when the incident ray is this side of the normal, where will the reflected ray be? On the other side, opposite side. Okay, reflected ray will be like this. Understood? Okay, so what will be the angle of reflection? Same thing, 50 degrees. And what will be the deviation? This is the incident ray for the second reflection. Extend. This is the final light ray. Deviation angle is this. What is this? This is delta 2. Is delta 2 clockwise or anti-clockwise? Anti-clockwise. So what will be delta 2 value? Anti-clockwise, positive. Okay, so 180 minus 2 into 15. 180 minus 30, 150. 150. Total angle of deviation. Okay, so plus 150 minus 60 plus. Now did you understand where the things went wrong? Tell me. Huh? Where? Huh? The formula is getting misleading. Huh? Direction. In the previous case, okay, so delta 1, delta 2, both the things are in the same direction, clockwise, clockwise, negative. Okay, so by means of this, what we have to conclude is, when, so both angles of deviation are in the clockwise direction, then 360 minus 2 theta is applicable. But here, both the angles of deviation are in the opposite directions. So when delta 1 is clockwise, delta 2 is anti-clockwise. When delta 1 is clockwise, delta 2 is anti-clockwise. Got the point? Now, okay, 360 minus 2 theta you obtained now. That type of equation can you obtain for this type of case? Try. 360 minus 2 theta you obtained by taking alpha, first angle of incidence, beta, second angle of incidence, theta, the angle between the two mirrors. Okay, 360 minus 2 theta we obtained. Like that, can you get one general equation in this case, where the angles of deviation are in the opposite directions? Will you get same thing, 360 minus 2 theta, or something different? So what will be that? What will be that? Come on, try. After getting that, this will be, okay, this is validated, validation, validity. You obtain a general equation for this. Now, you obtain a general equation for this. Exactly. The total deviation is equal to theta. Now theta is, I think you didn't work out. That's only by seeing that 60 that's equal. Now did you work out? Not last time, so last year, before the birth of Christ. Okay, at the time of Alexander. No, so those things I am not asking. Okay, now did you work out? Yes. What's the change? Always you go for, so the guessing no. Okay, so delta is equal to 2 theta you should get. You try. Okay, not even now. Okay, you try. And see, that's again. So you try on your own something. Okay, then so you will get interest. Okay. Okay, like this. Yes, now the time is, okay, 12:39. 12:40 almost. Okay, so 2 hours are over. Okay, those people are waiting. Now so I will be taking the class for them. Right? Okay, again our session is by 2 o'clock as per timetable. But okay, so 2 o'clock you try to be here. Okay, otherwise 2:30.